Our research project is based on adaptive multi-speaker diarization. Before we jump right into our research project, it is essential that we understand what speaker diarization is. Speaker diarization is the process of determining who spoke when. When two or more people are in a conversation, it is necessary to know who spoke from which timestamp to which timestamp. This can be used in several domains in combination with transcription services so that it can be more useful for analysis or any kind of uh, other user requirements. For example, it can be used in the business or medical domain to get transcription with speaker labels during the meeting process. And in addition, it can be used in places such as call centers for analytical needs and also in surveillance for surveillance needs. The domain of speaker diarization can be divided into modular systems and end-to-end neural diarization systems. The older systems used to be modular systems where separate modules need to be combined together and trained and evaluated separately to create a whole system. The current trend is to create end-to-end neural diarization systems where you do not have to plug and play separate modules. Rather, the whole system is trained and evaluated together. This will reduce the error propagation and is better suited for overlapping speech. These EEND systems can be further subdivided as offline and online systems. These offline systems can be further subdivided according to the number of speakers, whether the system works with fixed number of speakers or it can handle variable number of speakers. In our research project, we are using a system which is able to identify variable number of speakers and is in the offline domain and is a part of the end-to-end neural diarization system. The problem that we are tackling in our research project is that the current diarization models which use transformer variance to calculate the attractor numbers are the number of speakers. The transformer variants, they use quadratic memory complexity as the audio sequence length increases. Since the real world audio recordings are much more longer than mere seconds or a few minutes, it is very difficult when the transformer variants expect a large amount of memory to be used for the attractor calculation. This is the problem that we are tackling in our project. Since the current models that use transformers exhibit problems with large amounts of memory complexity, what we are going to do is replace one of the older models' LSTM layer with an RWKV based encoder decoder to get on par results to the current state of the art models. And in this scenario, we have implemented an RWKV based encoder decoder to our base model. Um, and we have evaluated the new model against the state of the art models. In addition to that, we saw that there were very low to nil amounts of data set for diarization purposes in the Sinhala and Tamil language domain, and therefore we created a Sinhala Tamil diarization data set named as Sita in order to improve our contribution to the speaker diarization domain. And in addition to that, we have also created a diarization pipeline in combination with transcription such that it will be able to give better output for the user using the model. Now, what is RWKV? RWKV is sort of a best of the both worlds of RNNs and transformers. Now, RNNs are very memory efficient as they handle data in a sequential manner and increase in an ON manner, whereas they struggle with capturing long range dependencies. In the case of transformers, they excel at uh, modeling long range dependencies, but they suffer when the memory complexity increases quadratically with long sequences. Now, RWKB is a novel RNN variant that is capable of capturing long range dependencies, and since this is an RNN, it is very memory efficient when the uh, data sequence length increases. Our solution architecture is shown in this slide. The LSTM encoder decoder in the EEND EDA model is being replaced by the RWKV encoder decoder. And the RWKV encoder decoder uh, is more efficient than the LSTM while being able to capture long range dependencies. Now, this result comparison shows a solution with the version 4 and the version 6 of the RWKV implemented on the EEND EDA model. Now, the current state of the art model is the diaper model, and it produces a diarization error rate of 18.89. Now, the models that we have implemented work better than the EEND EDA, the base model, but it does lack a little bit of uh, improvement compared to the current state of the art model. But when it comes to comparison of the GPU memory that is being used as the audio length increases, we can see that it works much better than the diaper model, which is the current state of the art model. Here, the diaper model, which uses the transformer-based solution for attractor calculation, uses a significant amount of GPU for a shorter audio length, whereas the model that we have implemented using EE and the RWKV works much better for a much longer audio sequence. Our next contribution is the dataset. The dataset is created using in the wild conversation, meaning it uses real world conversation that is taken from morning shows, competitions, and academic conversations, such that our resources for this dataset is widespread. The dataset size for the Sinhala dataset is 10 hours long, and that for the Tamil dataset it is 2 hours long. The number of speakers for each video vary from a minimum of 1 and to a maximum of 10 speakers in the Sinhala conversations, and a minimum of 2 and a maximum of 6 in the Tamil dataset. Our annotation process was such that the YouTube video was converted into WAV format files, which was then sent through the Pioneer model, which would create pre-processed timestamps, which we sent through the VIA annotation software to get approximate timestamps with the speaker labels. Then we manually annotated each and every timestamp with the speaker labels to get more accurate information. And this we converted into our necessary formats for our testing and evaluation dataset purposes. Our next contribution was the diarization pipeline, which was able to run in real time to get a stream of audio input and convert it into speaker labels and transcription, which would be much more useful for the user to understand. And in addition to that, an offline transcription result was also given to the user with the inconsistencies of the real time output mitigated. And the architecture for this solution was such that the audio sequence was taken by any kind of mobile or computer device and is sent to the server, from which the audio sequence is parallelly processed by a diarization model based on Python and a transcription model based on Whisper that is sent through a diarization LM to improve the accuracy to get the final transcription with the speaker labels such as the one shown here. And in addition to that, when the recording ends, the whole audio recording is sent through an offline Whisper and diarization solution with an LLM to get more precise and accurate transcription with speaker labels with the inaccuracies overridden and mitigated. These are our main solutions that we implemented as part of our research project. Thank you.